All right, so we have learned what parametric equations are. So now we're going to get into derivatives and that sort of thing. All right, so now this paper, you should have gotten this handout when you picked up your textbook. Okay, so this should be in the packet I gave you, but if it's not, this will also be posted in Canvas and you can print it out or take a picture of it on your phone or whatever on Canvas. Okay, so parametric equations, we've already learned what they are. We've learned how to write parametric equations given the Cartesian equation, and we've learned how to graph it by having the two equations x and y and just making a table. We've learned how to eliminate the t. So I've already done the first two. So what we're going to learn in this lesson is the next parts. We're going to learn, for this lesson, we're going to do number 2, which is finding the first and second derivatives, and these are the formulas on the sheet. And then we probably will do some of these, the highest, lowest point, right and left, vertical tangent line, horizontal tangent line. We'll do some of those. And then in the next PowerPoint after that, we are going to do how to find the length of the parametric curve, which is this formula here. So you have this sheet, again, like I said, in the handout that I gave you when you came and picked up your textbook. But if not, this paper will be posted on Canvas for you to print out if you've misplaced that. All right, so for this lesson, I just wanted to show you that particular handout before we got into this, just to know that that's there. So we are doing section 10.2, so the second target in chapter 10, which actually is our unit 2. We're only going to do tangents, so this section involves some other things. So we're doing tangents only on this particular presentation of parametric curves. So your outcome for 10.2a is I can find tangent lines of parametric curves. So we're going to do derivatives of a parametric curve. So again, what are parametric equations or parametric curves? It's a pair of equations, x and a y are both functions of a third variable, often a t, which is called a parameter. When it's trig, it's usually a theta. So you can have an x function that's in f of t and a y function that's in g of t. Now, as t varies, so as we change the t value, the x and y coordinates change. So remember when we did the t chart for the ordered pairs, that's what happened. And then you were able to plot those points and trace out the parametric curve. And you also had to trace out what direction we were going in. So just remember, that's what parametric equations are. So we're going to learn how to take their derivatives, which is not that bad. Derivatives of a parametric curve. So the first derivative here is dy dx. So same terminology as we've had before, except how do we incorporate that dt? So what I like to think about is algebraically, all right? If we have dy dx, we can take dy dx and we can multiply by 1 over dt and 1 over dt. So we can multiply by the top and the bottom by the same thing, which means we're multiplying by 1. But our form of 1 is 1 over dt, 1 over dt. All right. And so then what you get is you get dy over dt divided by dx over dt, which is exactly what this says, dy over dt, dx over dt. All right. So this is the derivative dy dx. Remember, dy dx is still the slope of the tangent line, all right? So how do we get the slope of a tangent line when the functions are written as parametric curves? So we know we have an x, which is written as a f of t, and we know we have a y coordinate, which is written as a g of t, okay? So what we do is we take the derivative of the y function first, and this is what the mistake is most that is done first when students are learning this. You take the derivative of the y function in terms of t, so take the derivative of this function and divide it by the derivative of the x function in terms of t. So you're just taking the derivative of this one and dividing it by the derivative of that one. And we're going to be in t's, so you just take the derivative in terms of t and you're good to go. Now, of course, that gives it the slope of the tangent line. Now, the second derivative, of course, we know tells us about concavity, whether the function's concave up or down. So in order to find the second derivative, which means you're taking d dx of dy dx, all right? So that equals this expression here. So again, you can do the same thing that I was just talking about. You can multiply this by 1 over dt over 1 over dt. You can multiply by the form of 1, multiply this times this. So when you do that, you're going to get d dt of this, so d dt of the first derivative divided by dx dt. So that's where this comes from. You're really just multiplying a 1 over dt, 1 over dt. So what does this mean to do? This means to take the derivative in terms of t of this equation that we already found over here. So this expression is going to be in t's when we're done with it. So you're going to take the derivative in terms of t of the first derivative, and then you're going to divide it by the derivative of this x function again. So that's all you do to find the second derivative. So you take the derivative in terms of t of the first derivative, and then you divide it by the derivative of x in terms of t. Okay, so it's pretty straightforward. So now what I want to do is in this PowerPoint, before we start doing examples of how to use this derivative, let's just practice taking derivatives. So I've got a few examples. So the first, so before we get into that, the first example I want us to do, number 1, we've got the function x equals t squared minus 2t, and then our y expression is t plus 1. And I want us to find the first and the second derivative. Let's just practice. Okay, so our first derivative, dy dx, that's the first derivative. So that's dy dt divided by dx dt. Because basically I'm just multiplying these by 1 over dt, 1 over dt. All right, so I need the derivative of the y expression. So the derivative of my y expression here, the derivative of this in terms of t is 1. And then I need the derivative of the x expression in terms of t. So that's going to be 2t minus 2. And that's my answer. Now, of course, I can rewrite this as 2t minus 2 to the negative 1 if I wanted to. Okay? So there's your first derivative. 1 over 2t minus 2. Piece of cake, easy, easy. All right? So now what's the second derivative? So now we want to do the derivative of this derivative, all right, of dy dx, which means I want d dt of, because remember I'm multiplying by 1 over dt, 1 over dt. So I want d dt of dy dx. Come on, pen. Divided by, I'm multiplying by 1 over dt, dx dt. Okay, so that's the easy way I'll remember it. So really all we're doing is taking the derivative of the answer we found up here for dy dx. We're taking the derivative in terms of t. So I'm going to take the derivative of this in terms of t. So multiply your negative 1 to the front. Then it's 2t minus 2, because you copy this over. Then you drop a degree, minus 2. Then we got to chain on the derivative of the inside. So all I did was took the derivative of the first derivative in terms of t's. Then you divide by the derivative of the x function up here again in terms of t. So we take the derivative in terms of t's. So I'm going to divide by the derivative of this. So that's going to be 2t minus 2. All right, now I can simplify this because this becomes negative 2 in the top. And if I take this downstairs, that becomes a 2t minus 2 squared down here, which gets multiplied by this. So this would be a 2t minus 2 cubed in the denominator. So this is my first derivative. This is my second derivative. All right. So you just have to remember what you're doing. You're taking the derivative of the y expression, the y function, divided by the derivative of the x function in terms of t's. And then to get your second derivative, you take the derivative of the first derivative in terms of t's and divide it by the derivative of the x parameter, right? That function in terms of t's. Okay, that's it. All right, number 2. All right, so number 2, what I want to do next. Let's say we have x equals t And we've got y equals t squared plus t. All right, so now let's find the first derivative. So dy dx, the way to find that is to do dy dt divided by dx dt. So just remember, you do the y function on the top. So the derivative of the y function would be 2t plus 1 divided by the derivative of the x one, which would be a 1. So that answer is just going to be 2t plus 1. So there's your derivative. So now let's find the second derivative. So now let's do d dx of dy dx, which means we're going to do d dt of the first derivative and divide it by dx dt. So I just need the derivative of my first derivative in terms of t's. Well, that's going to be a 2. Then I'm dividing it by this parameter, this one of the parametric equations, the x one. I'm going to take the derivative of that in terms of t's, which is going to be 1. So that means the second derivative is 2. Now, I know the second derivative tells me about concavity. So what does that tell me about the function since this is positive? That tells me that these parametric curves give me a function that is concave up all the time. That's what that tells me. All right, and then a third one. So I'm going to do a third one just to practice. So let's do one that has trig in it. So let's do x is, I hate when my pen's sloppy. Let's do x equals cosine theta, and let's do y equals sine theta. All right, so let's find dy dx. All right, dy dx is where we're going to do dy, instead of dt, it's going to be d theta this time because that's what letter we're in, divided by dx d theta. Okay, so instead of doing 1 over dt, we're doing 1 over d theta because that's what letter we're in. So it's dy d theta over dx d theta. Okay, so take the derivative of the parametric equation, the y one first, in terms of thetas. So the derivative of sine is cosine. And then you're going to take the derivative of the x parametric equation in terms of theta. So the derivative of cosine is negative sine. Okay. And then you know what cosine over sine is. That's cotangent. So this is going to be negative cotangent. So now let's do our second derivative. So we want to do the derivative of the first derivative. All right. So that means I want d theta of dy dx divided by dx d theta. Because remember, I'm doing 1 over d theta, 1 over d theta. So it's going to be d theta of this divided by dx d theta. So what does that mean to do? That means to take the derivative in terms of the theta of the first derivative. So we want the derivative of this. So the derivative of cotangent is negative cosecant squared. So I've already got a negative, so the negatives are going to cancel. So that's going to be positive cosecant squared theta. And then we want to divide it by the derivative of the x parametric equation in terms of theta. So the derivative of cosine again is negative sine. So now I can actually put this together because 1 over sine is cosecant. So this is going to end up being negative cosecant cubed. Because 1 over sine theta, if I can write, 1 over sine is cosecant. That's one of your reciprocal identities. So 1 over sine is cosecant. So this 1 over sine, I can rewrite that as a cosecant. So that's going to make me have cosecant cubed, which makes the answer negative cosecant cubed. So that's just some practice on how to take the derivatives. So this is your first video. So in the second video, we're actually going to apply the derivatives to actually solve some problems. So I wanted to break the videos up a little bit. So there's your first video.